Okay, fine. Yeah, thanks for putting together this workshop. Thanks for the invitation. Indeed, it sounded like a good idea. So I'm in a very challenging situation because Albert said before, you know, had everything turned out pessimistically, I wouldn't have given a talk. Thank you, Albert. Okay, let's see, you know, what I have to tell you about optimism and pessimism. Okay, so here's my outline. Why this project? Some story time. A lot of technical background that many of you in the audience know, so I hope I can be fast. And then I'll tell you about benchmarks. Okay, why this project? And so there was this time a few years ago when, you know, quantum computing hype was reaching a local maximum. Quantum computing just might save the planet is a screenshot I took from a McKinsey website in 2022. Around the same time, the German government decided to use COVID funding to give, who's laughing, to give, you know, to boost quantum computing for the German industry. And many people knocked on my and many people's doors here in the room, and companies asked, you know, for collaborative projects. And here's a typical passage from one of these grant proposals that, you know, the industry partner sent me, and they claim we will demonstrate how quantum algorithms will revolutionize our business processes. And that's basically a verbatim copy. And then before we submit, I always edit it, and when we submit, it says, we will explore the parameter regime in which quantum algorithms have the potential to revolutionize our business processes. See what I did there? All right, young people learn. Okay, fine. But now, but even that is not so super clear whether you can do it, no? So, yeah, so even the Morse code isn't obviously achievable because, you know, the industry partners, they don't really care about the problems that we know quantum is good at. They care, for example, for combinatorial optimization problems. And is a quantum a good fit there? We don't know. And if it were, how would we know? You know? And of course, these are typically NP-hard. So no general efficient quantum algorithm is expected to exist. But there's also promising heuristics, you know, like both quantum and classical. So it's very difficult to actually make an informed statement whether we have, you know, some kind of advantage, because we're lacking the quantum hardware for large-scale benchmarks, which is, of course, you know, the gold standard by which these heuristics are usually assessed classically. Okay, so then we are looking for a project where we could maybe make an informed statement in the end, and yeah, that I felt comfortable submitting, even with this kind of like moderated down promise. Okay, and now I will walk you through a bunch of technical preliminaries to tell you how we identified the project, and then I'll tell you how it turned out. Okay, so technical background number one is quantum semi-definite programming. I think I will, you know, be preaching to the choir. I'm not sure whether there's anything I can tell you guys that's new. But anyway, let me go through it very quickly. So semi-definite programs, which are SDPs, optimize linear functions over the set of positive semi-definite or PSD matrices. So it's very confusing because SDP and PSD, you know, they're mostly the same letters that mostly stand for the same words, but not quite. Subject to linear constraints. So here's, right, you know, the canonical setup of a semi-definite program. Of course, you know that. They are formally classically efficient, but very expensive in practice. So it's one of these problem classes where a polynomial speed up would be welcome. Okay, and in fact, people have thought about quantum SDP solvers for about a decade. There's this, it's a big field, or like a moderately big field that started with Brandão and Swore in 2016. And so the idea is to represent the positive semi-definite matrices natively as a state, instead of writing out, you know, the matrix elements in a classical computer and see, you know, whether one can build an algorithm around that. Okay, here's a very high-level idea, and one of these detailed ideas I will explain to you in more detail a bit later. Okay, so the idea is to create the PSD matrices as exponentiated Hamiltonians using a quantum Gibbs sampler, and then the objective value and violations of the constraints, these are estimated from measurements on those Gibbs states, right? And then you get information about where you are, and then you update your Hamiltonian with the goal of converging to an optimum. So the good is that the matrix size does not directly enter, right? Because you never have to write out the matrix elements in memory. It's only the complexity of Gibbs sampling that does enter. Of course, that indirectly might also depend on matrix size. That now very much depends on the problem details. The bad is that the data is stored in a kind of analog way, and so you have to statistically estimate all the quantities, and that's extremely expensive, obviously. And it uses difficult to realize primitives like quantum RAM, for example, for many models, depends on the details. So that isn't exactly a NISQ algorithm. All right, so what does one might expect? Where are these quantum SDPs? So what's good? Where will they not be good? So they have a very favored scaling in the dimension n. In fact, it doesn't directly enter the problem if you want. They have a very unfavorable scaling in the precision you want to achieve, because again, all quantities have to be estimated statistically. And so now we have to find a problem that, for which this is not a big disadvantage. And in fact, if you look at the original paper, here's the abstract of Brandão and Swor, and okay, so the noise dependence is here, like the precision dependence is here, and they just say poly. They don't, say exactly what they mean by poly. And I'll show you in a second why they might be, a bit coy to actually, you'll see. All right, okay, that's ingredient number one. Everybody got that, no? Now, so the big challenge is now we have to find a problem where this very bad scaling of the precision doesn't kill us outright. And so for this, we look at another set of well-known primitives here, namely QUBOs, SDP relaxation, and an algorithm I've been taught by my Dutch PhD student to pronounce Williamson. Is that correct? No. Okay. Well, thank you then. What's the pronunciation? Humans. I think actually that's what I was taught. I just forgot. It comes with age. Okay, so QUBO is quantum information's favorite NP-complete problem, quadratic unconstrained binary optimization. Of course, you've seen it many times. Right. So yeah, where we want to. Okay. I was confused because it says real numbers here, but we are restricting to binary variables here. All right. So we have a quadratic function in binary variables, and we want to, let's say, maximize it. Some people want to minimize it. We are optimistic because Albert asked, is Albert here actually? Oh, there you are. All right. Okay. And okay, so then let's rearrange this thing, kind of trivially to see, whether there might be a good heuristic or like a good, approximate approach. And so this objective function, it's quadratic in the variables, but of course you can take the vector here of the x and form the outer product, and then it becomes linear in the outer product. That's how you pass from state vectors to density matrices in quantum. And so we can alternatively optimize over the convex hull of these rank 1 projections, where we take rank 1 projections onto vectors whose components are plus minus 1. And now that's a convex polytope, so that sounds very good. We've just converted an NP-hard problem into a linear, into an LP, a linear optimization over a convex polytope. Of course, the downside is that this polytope is very complicated, and so the hardness from this point of view stems from the difficulty of describing this polytope. And so the idea is to replace it by something that's slightly larger but more simple to describe. And so here's how it works. It's the SDP relaxation. All right. So all these outer products, they are positive semi-definite vectors, obviously, with positive semi-definite matrices with main diagonal exactly equal to 1, because let's write it out in a basis. And so the idea is now to just keep these two properties and forget about all the rest, and optimize over the set of matrices compatible with those constraints. Okay, now we got a maximization of a linear objective function subject to linear constraints over PSD matrices. And what we've done is we've taken the polytope and kind of blown up the faces a little bit. So it's a little bit bigger, but much easier to describe. Okay, this gives an upper bound on the optimal value because we are optimizing over something larger, but it gets better. Namely, if you have such a solution, you don't just get an upper bound, you actually get an approximate combinatorial solution out by a process known as randomized rounding. So you take the solution of the semi-definite program and you construct something combinatorial by first taking the matrix square root and then projecting it onto a Gaussian vector and then take the component-wise signs. Whatever, you can analyze it in a few lines of pen and paper. It's not so difficult. And the big news here is that a guy who the local audience taught me to pronounce as Human, Oh, it doesn't, there's no S here, so that's even misspelled. Oh no. Okay, as Humans, sorry for that. Showed that this actually, that gets you up to the optimal solution within a dimension-independent factor for the optimal value. So it's a very good heuristic, and in fact, or like a very good approximation method. And in fact, there is a conjecture in complexity theory that for many problems, this gives you the best approximation to this NP-hard problem that is achievable in poly time. So it's a very well understood and easy to analyze, good approximation method over which you have very good analytical control. Okay. All right. So now the idea is to combine these two things. That's not our idea, but this has been out in the literature, as I will show you in a minute. Okay, so here's the summary of the situation. So, okay, so the performance of quantum heuristics for NP-hard problems is very difficult to assess. But semi-definite programming methods are conjectured to give the best possible tractable approximation. Their performance is well understood analytically. Quantum implementations could overcome the unfavorable scaling in problem size. But also, because we're just looking at an order 1 approximation and because we have this rounding step in the end, it means that precision might not actually be so crucial. You don't have to solve them to a very high level of precision. So this sounds like a good fit. So then there is the hope for a bullshit-free, non-asymptotic, well-justified quantum advantage for a relevant problem class. That sounds like a good idea, no? Don't you agree with me? No, that's... I think I was very high, like I didn't feel dirty submitting this to like the federal ministry or whatever. Okay, and it's even better because there's prior art. So like the basic idea isn't even ours because people have worked on this before. And Fernando, Richard, and Daniel have written a paper on this with basically the same motivation I just told you. So the only thing is it's still very much in the proof of principle regime. Because here's their main result, and they got the various scalings. They have a classical and a quantum version of their algorithm, and they call their precision parameter mu, and here they make the exponents explicit that before were just poly, and you can see like 28th powers or something appearing. Even in the classical computer case, 12th powers appearing. So these are, in principle, quantum advantages, but of course it's completely unclear whether they work practically. So we got ourselves a project, namely, we have now a problem for which there is a proven quantum advantage, compared to the relevant state of the art. And so the question is now, at which problem size will this proven advantage manifest? Because that's, of course, what the industry partners are actually interested in. Fine, we got ourselves a project. So we hire a PhD student and ask him to do that. Yeah, okay, I can tell you more stories about this, but maybe if I have time later. Okay, so now what should we do? We could now just take their paper and let the student code it up in Python and kind of estimate the quantum advantage and then report it. But that would be very unfair and would maybe not tell us very much because Brandão, Kueng, and França, they obviously stopped after obtaining a proof of principle result. They put zero effort in actually optimizing it for non-asymptotic values, and we know it because Richard was one of our co-authors, so he's saying the same thing. So if I benchmark the algorithm as presented, it wouldn't be meaningful. So before we knock down the quantum algorithm opponent, we first have to build the opponent up, yeah, so that it's that any negative result will be meaningful. So step 1 is to optimize their algorithm, which is called Hamiltonian updates. And only once we've documented that really we've squeezed the last bit of juice out of that algorithm, only then can we benchmark. And if the benchmark then turns out to be unrealistic and negative, then I think then we have a meaningful result. But that's only step 2. So ironically, even though in the end the project will tell you that the quantum algorithms here don't really work, the main effort we put into the project was to actually spruce up the quantum algorithm before punching it in the face. That's very violent imagery. I don't know why I'm saying that. I'm not a very violent guy. Okay, so let me tell you then Hamiltonian update their algorithm, what they did, and where there were screws to be tightened. Okay, so here's now it's slide 1 of 6. I took the slide from a different talk where I had a 1 hour slot, so I will not maybe actually mention all 1 of 6, so I will tell you some key points of this algorithm. All right, okay, so that's the algorithm we start with. No, we are the semi-definite program, we are optimizing over semi-definite matrices with all ones on the diagonal. And we will reduce it in a number of very simple steps. So here first we have renormalized. So X is, in my convention, a PSD matrix that is super normalized with trace n. Then, of course, if we want to put it on the quantum computer, we divide everything by n. Now we got a state rho. And also, instead of optimizing, we will solve a sequence of feasibility problems. Namely, we choose a candidate gamma for the objective value and see whether that's feasible or not. And then using binary search, if we can do feasibility problems, we can optimize. And also, of course, we're going to epsilonify everything, because everything has to be estimated statistically. We can only, upper bound all the constraints and violations and objective functions by some epsilon. Okay. Right, then we use a Gibbs state parametrization. So we don't actually ever optimize over PSD matrices directly, but over Hamiltonians, and use a Gibbs sampler in the background to prepare the Gibbs state. We initialize at h equal to 0, so we initialize at the maximally mixed state, and then try to improve in an iterative way. All right, so how do we actually, now that's the core of the algorithm, that's why it's called Hamiltonian updates, because it's updating the Hamiltonian. So that's what you do. So here's the geometry. So at some point of time, you are at an iterate row 1, for example, and you want to see whether the objective value is smaller than some threshold value gamma, and so that's like a geometric situation. Is you want to go, there's some hyperplane in the space of PSD matrices. You want to go here to the negative side, and you check whether you are on the positive side or not. If you're on the positive side, what you do is you update the Hamiltonian by adding a contribution that is proportional to the violated constraint. And then using StatMech intuition, this makes larger values for this violated constraint energetically more expensive, so it will reduce the expectation values, so you move closer to the feasible region, and then you iterate that. That's basically the algorithm. Yeah, that is for cost update. There are also constraints that need to be updated. The constraints are only the main diagonal equal to 1, which you do exactly in the same way, except now you're actually doing a full computational basis measurement. You can already see statistically that's going to be very expensive. And in the end, the running time of the algorithm is dominated by these diagonal updates. Okay, so the one thing that is really non-trivial here is about termination. So let's say you do an iteration after an iteration, and the things, the values get better and better, but at some point you have to give up and declare the problem to be unfeasible. And so one of the main theoretical contributions of the original paper was a solution to this problem. Okay, so the assumption is you assume that there is a feasible state rho, and you track the relative entropy distance between your current iterate and the feasible state you assume exists. And so now it's an elementary fact of relative entropy that the relative entropy distance to the initial uniform state is upper bounded by logarithm of the dimension. And what B, K, and F prove is that if a constraint is violated by at least epsilon, then this StatMech intuition can be made precise and reduces the distance by something of the order of epsilon squared, which they compute. And so if no solution is found after epsilon to the minus squared steps, the problem must be infeasible. And it's a quadratic scaling, not great, not terrible. Okay. And then in the end, they round, and rounding is more difficult because the rounding guarantee of months with an S that I don't know. Also, Williamson's is also a common name. I suck at spelling, so don't hold it against me. Yeah, it's for exact diagonal constraints. Actually, we only enforce them approximately, and then it actually gets much worse. So it still works, but the rounding, but the bounds become much worse. They're quite sensitive to the error. So that was the original algorithm. So I actually explained it to you, all 6 steps. All right, now before yeah, before benchmarking how it works on real-life problems, we sat down, and by we I mean the student, Fabian. Thank you, Fabian, for 1 year or so, and really, optimized it. And here's a long list of improvements, and I don't want to explain them all. I want to kind of like inspire confidence by you in me that we actually gave our best. Let me quickly give you an overview. Okay, so there's it's an iterative algorithm, so there's a learning rate, which initially in the original paper was fixed. We made it adaptive. And so, if there's big violations, we update it faster. Okay. Then we had another PhD student on the project who worked before in classical machine learning, and he told us you got to add a momentum term, which apparently in gradient-based optimization, you don't actually walk along the gradient, but the gradient just changes the direction of your flow and you keep some momentum. And I said, cool, but why should that work? And he said, I have no idea, but everybody's doing it in machine learning. And I said, this can't possibly work. No, the gradient gives you the best information. And then he didn't listen to me and added the momentum term, and bang, things got better. I have no idea. Don't ask. Right. More improvements, blah, blah, blah. Aha, switched from relative entropy tracking to free energy tracking. We read our StatMech textbook and found some better bounds. We improved the bound for impact of noise on rounding. We updated to newer GIP samplers because the GIP sampler community doesn't stand still. Every few years they optimize the bounds, so we, updated it. Okay. So maybe the free entropy tracking. Okay, I have not so much time, but maybe we can have a brief look at this. So you can, right? So you can expand the relative entropy, and if you do it, then there will be one term appearing here, which is the free energy of that Hamiltonian at inverse temperature 1. And okay, so it starts off at negative log n if you have 0 here, so the maximally mixed state. And so it's easy to see that if there is a feasible state, then Hamiltonian updates will always have a free energy that is negative until, or else will have reached the feasible solution. And so now what we can do is we can link the free energy change under an update to the degree of the violation of the constraint. And so this makes it much better because if there's a big constraint violation in the beginning, then we can now account that we move much closer to the target, whereas the original algorithm didn't do it. So that gives a big improvement to reduces the number of iterations needed a lot. Okay, good. So now here's our summary. Like these will now be tables that kind of again tell you in a trust me kind of way, that we actually tried our damnest to make the thing work good. So how can you see it? So here's a feasible instance. There's an infeasible instance. Here's the original algorithm on some kind of sample problem, not too big. And okay, so we have number of iterations, like hundreds of thousands or low single-digit millions or tens of millions. And then we implemented the various improvements and saw the number of iterations go down. Adaptive step size, dang, whatever, 2 orders of magnitudes. Entropy tracking here doesn't do anything for the feasible instances. For the infeasible instances, it gives us, 4 orders of magnitude. Momentum, I don't know why, but it, shaves off another 25% or 30%. So, we went from millions to dozens of iterations. So yeah, so that's, by benchmarks, we also improved the exponents in the numerical bounds. Now it says nu, not mu, not delta, not epsilon. There's different error metrics for the purpose of the talk. They're all the same. And you see that the exponents go down 8 to 6, not very radically, 28 to 15, I don't know. But of course, these are, actual bounds, and so the numerics seems to be much, much better than these bounds. Okay, so I think, Albert told us we have to have some uplifting news. So the uplifting news is that things got much better, and I think the classical version of the algorithm might actually now be competitive, maybe. I don't quite know. So, of course, we also ran like standard SDP solvers as a comparison, and in the end, like the Python code of my student was not completely super much worse than what an off-the-shelf SDP solver could do. So that's good. No, maybe if you're very ambitious, you can now turn this into good classical algorithms. But now, of course, we wanted to, yeah, I come to the actual core of my talk, but also to the end of my talk, because there's not so much to do now. Now that we have, something that is, propped up, not a straw man to attack, we can now run a quantum benchmark. And for this, what we do is we ran the algorithm for random problem instances, that are already challenging for SDP solvers. So what we did is we implemented it classically. We did all the iterations. We logged all the parameters of any quantum subroutine that would have been called. So we logged the spectral information of the Hamiltonian when we called the Gibbs sampler, for example. And based on this, we estimated the number of quantum gates based on the state-of-the-art implementation. That is not a rigorous lower bound, because of course we don't know even classically, humanity sucks at proving lower bounds to computation problems. So, we took best known state-of-the-art implementations as a benchmark. And then we've been extremely generous to the quantum version. Of course, it's a very difficult problem to estimate the quantum runtime in a meaningful way, so we just gave all the advantage to quantum. So we only counted 2 qubit gates in the state-of-the-art implementation, or the single qubit gates we ignored. We assumed no error correction overhead. In fact, we only counted the cost of estimating the violation of the diagonal constraint. Everything else we just thought the quantum computer can do for free. Whenever we call, for example, the Gibbs sampler, we use the best known bounds on the runtime that sometimes depend on information like spectral information of the matrix that might not actually be available when you call it in real life, but we just gave it to the subroutine, whatever. Yeah, we pretended that the Gibbs sampler returns exact results, which in fact it doesn't. Okay, and so now we have to plot the results somehow. It's not so super clear how to visualize it, because we're not doing asymptotic complexity theory. We are, it's a finite-ary algorithm. And so here's what we came up with. If you think it's unfair, please tell me. I think it's, a meaningful way of seeing where we are. Okay, so what we did is we took the classical running time on a laptop that was cheap enough that I bought it for the student. So yeah, it was a good laptop, not a very good laptop. And then we divided the classical running time by the quantum gate estimate. And so what we get is like a time scale now, so that if 2 qubit gates of a quantum implementation, they would have to be at least as fast as this quotient, so that the quantum computer here would break even with the student laptop. It's not very scientific, I have to apologize. No, I used to do theorems for my living. Now I divide estimates by constant that depends on the make of the laptop. But I think you will see in a second that it doesn't really matter, I think. Okay, so now the quantum range. Now that's like the big plot in the paper. I have to explain what this means. So that's the classical computation time in seconds on the student laptop on the x-axis. That is the 2 qubit gate time that would be required to break even. Right, so then we took random samples of problem instances and estimated them in 2 different ways. Like, don't ask, do ask for the details, but for now it doesn't really matter. And so in fact, I should plot it in this log plot here, log plot, where these are the instances we could estimate. These are the extrapolations, and what I have here is the shortest gate time we could find in the literature of any quantum gate ever published, and it was a single qubit gate. And so, we would have to, if we could get this down from 10 to the minus 9 seconds to 10 to the minus 21 seconds, then a quantum computer would have beaten the student laptop. That's, of course, completely ridiculous. I mean, we're not going to achieve that. So we can see, of course, we know asymptotically there is a quantum advantage. It's been proven. No, Fernando proved it. No, I shouldn't doubt it. And it's true. You can extend these estimates, and at some point they will hit, any constant, in particular this. But now there's a log plot. I don't know. So now, of course, I don't feel so bad anymore for using like putting like the Lenovo carbon, whatever constant into this plot, because it doesn't really matter. No, you can shift this a little bit, but I think, yeah. I think there is like no realistic regime of a quantum advantage that is visible after more than 1 year of work by a PhD student, with the backup of a team of experts. And so, yeah, that's maybe not a rigorous proof that there is no quantum advantage, but I think it kind of sends a clear message. I've learned, again, on the uplifting side, I've learned a new word, namely the term a galactic algorithm. A galactic algorithm, apparently in computer science, is an algorithm that is provenly the best, but achieves this advantage only for problem instances that are so large, so galactic, that they will never be relevant in practice. All right, so summary, it's tough to estimate non-asymptotic running times of quantum algorithms. Yeah, okay, but it's also tough to find reachable regimes where quantum advantage manifests even if it's asymptotically proven. But I did think it sounded like a good idea. I don't think we set ourselves up for failure. I think we gave quantum a fighting chance, but it didn't pan out this time. All right, that's it.
Right, thanks, David, for the fun talk. Maybe we have time for one quick question. We're running a little bit behind schedule.
Yeah, so coming back to the laptop plot, I was curious. So I guess the gates the gate speed that you sort of need are also more than 10 orders of magnitude faster than the fastest classical logical processing.
Yeah.
Link. So if you had the quantum computer which could do this, then also just running irreversible logic, the thing you would do on the laptop would also outperform it.
Yeah.
So doesn't that suggest that there is like there should be something better that you can do on the quantum computer than
Yeah, that's a good point. I know. So the quantum time is super dominated by the statistics required to estimate the diagonal violations. And that's just statistics, not super sure what you can do. But it's true, there's another consistency question that we haven't asked ourselves, namely, I said that's when the quantum advantage manifests compared to the student laptop, but you say at the same time, obviously, classical is also faster. So I'd have to think about this, whether, it's going to be even more devastating. So that's a very good point. Yeah. There's one desperate hope, if you want to really spin some positive spin on it, because what dominates the quantum runtime is statistics. That's of course completely parallelizable. Yeah. So if you had 10 billion quantum computers, then they would parallelize in a way that's not so obvious whether it would parallelize for the classical, except of course at some point you can just search the search space exhaustively. So maybe if you look at a parallelizable kind of minimum runtime, maybe then quantum is better. But yeah, no, but it's a good point. So yeah, so the question, maybe the classical advantage is pushed out even further if you give the same advantage to the classical computer. It still has to be there because the asymptotic scaling is still better quantumly. Yeah. Oh no, you made it worse. All right.
Maybe one other quick question, if there's any. Okay, if not, then let's thank the speaker.